So, now we will start another type, that is photochemistry of pi star system. So, in pi star system we will be dealing most of the time with your alkenes, dienes, your aromatic systems, all these things we will be dealing with pi star. But before getting into the reactions, we will just simply understand how this pi star photochemistry works. Okay. Just we will put some thought on it, then we will get into the reactions. Right. See, if you are if you have an alkene, type of an alkene, okay, and you photolyze this. What happens is that, yeah, you know this state, that you get an type of good pi star excitation. Right now, I am not introducing any word singlet or triplet. Okay, I am just taking an alkene, I am photolyzing. Okay, you get a type of excitation pi star. So, I am saying that this can be a pi star excitation. So, how this will be in the singlet state? Mostly this should be in planar. Okay, you have a system 2 carbon with your pi systems like this. So, it will be in planar. Okay. You know why it is, because your Frank codon does not allow it to do anything during the excitation. Excitation process is so fast, whatever how it is in the ground state, it will be in the same way in the exciter state. Okay. So, people call this as a Frank codon planar structure, but normally you can think it is planar. Now, this is the interesting part of your pi star system. What happens in once it is there, the excited state in the planar, it undergoes a little bit twist on the carbon 90 degree. Okay. It undergoes a 90 degree twist. For example, if I make this part a little bit, it gets a nice 90 degree twist, okay, in the excited state, and you get a, you call this as a relaxed, people call this as, since you say it is twist, it should not be allowed, but that is why you call it as a relaxed twist state. It is like comfortable there doing this twist. Okay. Why, I will explain you. Basically, the energy requires to move from planar to relaxed to states is like only 2 kilocalories per mole, not more than that. So, it needs only this much of energy to do this, maximum 2 to 3 calories, that is all it needs. Okay. This is the difference between your n pi star reactivity and pi star reactivity. Okay. Once it gets to excited, it will be in a planar, but immediately it undergoes a twist in the which is a 90 degree type of rotation to give you a relaxed twisted state, fine, and that is 2 kilocalories per mole, that energy requirement. So, this you have to remember first before we are getting into any excited state chemistry. Okay. The second point is that, keeping that in mind, if I take my alkene and do the photolysis, yeah, as you said that it can undergo a singlet. Okay. S1, then it undergoes an intersystem crossing. If it is, okay, it is not that must, if the energy profile allows it to undergo an intersystem crossing, it undergoes an intersystem crossing to give me a triplet, right. Now, I said that this planar, when it is planar, it undergoes a type of twisted, right, it undergoes a relaxed. Because of this, these two electrons which are away from each other, okay, they come to the same orbital, they fall like this, they become like, mostly if you see, that is, it becomes like this, fine, because of that twist, the whole of the electron will flow to that carbon, okay, and they become, one end will be becoming more negative and another end will be more positive. So, so how it looks like, what you call this normally, a system which has a negative and positive zwitterionic. So, that is very important. So, see this chemistry particularly clearly differentiate your singlet and triplet. When you are talking an alkene in a singlet excited state, any chemistry, it should work as a zwitterionic. You can push your 2 electrons happily, okay, plus or minus. And but if you do intersystem crossing and get to triplet, then you are going to do radical chemistry. Here it is normal chemistry which you do with your carbon anion, nucleophilic, electrophilic, you push your 2 electrons together, right. That type of arrow you can use when you are talking about your singlet excited state. But when you are talking about triplet, again it becomes a radical chemistry. So, what you can see from zwitterionic, what are the reactions you can think of? Any reactions which you can see? There are many, I will tell you, but what do you think, if I get a zwitterionic, what type of reactions I can think about? Yeah, one, you can think about your carbon anion reactions, right, because you have a carbon anion, you can think about any carbon anion reactions that is there. You can think about your carbonium ion reactions. What are the carbonium ion reactions? You can, if you have a methanol, then you know you can do rearrangements, right. Carbonium, if you are creating a carbonium ion, then you can do rearrangement, that type of reactions you can look for. Then you have a minus plus, another minus plus is there, you can do additions, right, dimerization type of reactions. Another main reaction is, which you are going to see most of the time when you think about alkene, is cis trans isomerization. See this reaction, cis trans isomerization, this is very predominating reactions of alkene chemistry, cis and trans, okay, fine. But in some way you are going to triplet, okay, that means you are using sensitizer, you are moving to triplet state, okay. Then what chemistries you can think about? Triplet, again it undergoes nice cis and trans, because that is not going to stop it, okay. Even if it is a radical, it can do a cis and trans, right. It can undergo dimerization, all right, that also you can see. And then you can see all your n pi star reactivity, right, because it is again radical. You can see all your n pi star reactivity. What are they? Hydrogen abstraction, you can look for hydrogen abstraction. You can look for cleavage, energy transfer, electron transfer, so you can see all this cluster of reactions happening. From singlet you can see carbon anion reactions, carbonium reactions, dimerization, cis trans. From triplet you can see again cis trans and dimerization, followed by all your n pi star reactivity, that also you can see, because it is more like a radical chemistry. But anyhow, this is not going to happen most of the time. Okay, these are reactions which you should know. We will come down and we will sort it out, what are the reactions which is dominantly going to happen when you do an alkene chemistry. Okay, but these are the reactions you should know that it can happen. We will just see the energy diagram of alkene and see that whether we can sort these reactions, whether all these reactions going to happen or some predominating reactions which is going to happen, that we can think about. So, you know pretty well how to write your alkene. You have an SO and then you have a excited singlet, and you know that you have a triplet for alkene, any alkene system. The one big thing you know is what? That your energy gap of an alkene most of the time is comparatively larger than your carbonyl, that is n pi star reactivity. Most of the time your pi star energy gap is always larger to that. So, what it says? It says that my intersystem crossing will be very slow, right. So, energy gap is large, intersystem crossing is very. So, this can be one observation. So, then what it says, then if I take my alkene and do the chemistry, I am going to see chemistry only from the singlet. Okay. So I am going to see my chemistry only from the singlet. What are the chemistry which happens from singlet basically? Just now we saw cis trans, right. Then it is okay, carbonium and carbonium, which you know, but these are the two main chemistry which happens from your alkene. Okay. So, you should know sometime it undergoes cis and trans isomerization, sometime you end up with your dimerization reaction. These are the two predominating reactions when you think about pi star chemistry. Yeah, other reactions all happens, that is fine, but that needs some sensitizer. If I put sensitizer, I can take to triplet, then I do that chemistry. But if we take alkene and directly excite an alkene, then I will be putting my mind on cis and trans isomerization, or I will put my mind on dimerization. Fine. So, these are the two reactions which we will discuss in detail. We will discuss cis and trans isomerization, then we will discuss dimerization. Then there is one chemistry which is PET chemistry, which you electron transfer, which you have studied, that also happens in alkene, that we will discuss. So, these are the three main reactions we will discuss on pi star. Okay. So, once we finish pi star, then we will discuss something about your singlet oxygen reactions and some rearrangement. So, that is how the photochemistry ends up. Okay. So, we will start then from cis trans isomerization. So, this is your what structure it is? What is this compound? Very good. It is a trans stilbene. So, if I photolize this trans stilbene directly, okay, Then see, you know, trans are much more stable, that you know from your. So, if I photolyze this, then you end up with, in photochemistry you can get up your so you can take your trans stilbene, photolyze, you end up with a cis stilbene. But most of the time this reaction is not like moving from trans to cis. You will always end up with some sort of equilibrium happening around this trans to cis. Okay, then from cis to trans, then trans to cis. Okay, it's not like this chemistry you call as photostationary state. It goes to a state. Okay, then again it see you see both the molecules. You think they will have different absorption. Whatever wavelength in which this is observing, the same wavelength this will also observe. Okay, they are not going to have different UV absorption. So, once you are no, their epsilon might be different. Okay, most of the time what happens, see, I cannot have a wavelength which is like exactly 285, another 287. Okay, I am talking about a wavelength of range. Okay. So what happens, trans to cis, then cis absorbs, then gives to cis trans. So, you always have a photostationary state. That is why you most of the time you cannot think of full conversions, okay, in this chemistries, but you have always this up and down happening. But there are reactions where you can push from trans to cis and get the cis out of there. Okay, we will see that examples also. So, we will see how the mechanism of this works, okay, and why this reaction has been done and people have isolated cis stilbene, but we see how it is. If you see the mechanism, for example, this side I am taking my trans stilbene, okay, I am photolyzing this. I can write how it looks like hydrogen phenyl, and this way it will be phenyl and my hydrogen, right. So, I get like this if the system has trans. You think if the system has a cis, then how it will be. Then if I excite this guy, so I get two type like this if you have a cis and trans, right. You know, once it gets to the excited state, it undergoes a relaxed juice form. So, it undergoes a type of rotation. So, if these two are undergoing a type of rotation, you will end up with a common intermediate. Okay. So, just turn this around. Okay. In both the case I can turn around. So, I can get my hydrogen phenyl, and both the case you will get a type of a common intermediate. Okay. This intermediate can give me my cis and trans. Okay. So, that is how it keeps on flowing. Okay. You take it to cis, then it undergoes, because of this relaxed juice form, it comes back from both the cases, it can come back to a common ion intermediate, which depending it can move this direction to give me trans, and it can move this direction to give me cis. Okay. But once you do photolysis, you have a trans here, you have a cis here. Okay. So, which will absorb light more? Trans. Why? Yes, extended conjugation of trans. So, what helps extended conjugation? more. So at the end what you get? Yeah, at the end. Yeah. That means basically what happens is that molar absorption coefficient, that is your epsilon, okay, which is very important. That tells you how much a molecule can absorb, okay, which you have studied in your UV, right. Your epsilon max for this is, for trans, is around 16,300, okay. But if you see the epsilon max of your 6, it is around 2,880. So, this where it is very important, that when I shine a light, because trans gas, it can absorb so much, because it has a very good epsilon, that means its molar absorptive capacity of absorption is greater. So, it can absorb all the light, even cis is in the same wavelength. So, cis absorption will be less and this trans absorption will be greater. So, that is why you see the conversion happening from trans to cis 95%. Okay. That is very important when you take. If your system which has trans and cis same absorption, then you will be getting only photostationary state. You go from trans to cis and you get to cis to trans, but that also important. Many application also came out of it. You can have a system which can goes to trans to cis and do some chemistry there, releases a molecule or can bind it and then leave it off and come to trans. So, many other applications also made from that chemistry also. So, it is nice that you can move from trans to cis and cis to trans. Looks like to be a simple chemistry, okay. You take a trans and you do cis, but lot of applications are coming out of it. Yeah. Fine, okay. Now, what we will do, I will start understanding can we draw cis and trans, because sometimes it is very hard to draw cis and trans. Okay, we will see that whether we can draw cis and trans. For acyclic systems, it is nice to draw. First, we will take an acyclic system, which is easy to draw cis and trans. Then we will go for a cyclic system and see whether we can draw cis and trans. Okay. Take a first example, which you guys know to this I think it's easy to draw, but just as an example I am saying. Do a photolysis. As try to draw the trans structures or the cis structure. Just we build up how to draw, because I think you know the photolysis, so it is nice to draw the structures now. Without seeing the board, you can draw by yourself. Yeah, this is nice example. So, it looks to be simple to draw. Okay. See, another important it's your azo compounds, right. You have seen many times azo compounds are whenever someone gives you azo compound, you always have in mind that it undergoes a cis and trans. Okay. Azo compound is very good for that. Lot of very nice application comes out of this cis and trans of azo compounds. Otherwise, what happens if you photolyze them for a long time, you can also see some chemistry of nitrogen going out. Okay, that type of chemistry also seen in azo compound. But simple, you take an azo compound, you photolyze, you end up with a nice cis and trans. Okay, this is easy to draw. Now, we will take one natural product and see how we can draw cis and trans. Okay, just your natural products which you know. What is this compound? Where you have seen this compound? Somewhere you have seen this. Yeah. To make? Somewhere you have used this for, studied this compound for making your vitamin D. This is pre-vitamin D. Okay, before step of vitamin D. You have seen this pre-vitamin D. Okay. Now, if you fertilize, yeah, draw me the other form. So, you can say this is how we are thinking to draw that. That is more important. That is why I was looking. This cis trans looks to be easy when you take a simple molecule, but the best way of drawing is how you can understand them properly. That is what I was looking for. You get another good natural products if you do the cis and trans. What you get? You take a pre-vitamin D, and if you fertilize pre-vitamin D, you get a nice natural product. And finished. So, just we will check whether what way your written, see whether is as any. Better way of looking, na? How you want me to write the OH now? It will be in the same plane if I down. So, shall I like this, or I have to keep the OH in the same symmetry? That is what I want you to visualize now. You are just taking a cis and trans. Now, you are just moving across. Okay. So, are you forgetting your OH, or it will be in the same symmetry? No, I am just asking you. There will be change or there will be no change? There will be change, na? Yeah. So, these are things, minute things you have to keep in mind when you are just looking about your double bond. Okay. So, these are the systems. That is why I said little cis and trans writing is little bit. What is this called? Okay, it is what molecule? Basic. It is a what type of? It is an alkaloid or it is what? You know, identify alcohol, alkaloids, terpenes. It is a terpene, or it is sterol. Yeah. Then where terpene comes here? These are known chemistry. You take a pre-vitamin D and you fertilize, you get testosterone. And even you can cyclize this, because that you have studied this natural product synthesis. You can cyclize these rings, you can open them, con-rotatory, dis-rotatory happens, then you end up with pre-vitamin D, that will fertilize to give you testosterone. Yeah, whenever you flip molecules, please see what are the other any chiral molecules are there, where you have to keep that also in mind. Okay. Fine. These are some good examples of your even I can think of one example, which is like azo. This is easy to draw, but just to make you that sorry, there is no end there, fine. Don't want a trans, I can take a cis of it. So, this is imine, alright. Imine also undergoes, when you fertilize, it also undergoes nice cis and trans, just for your knowledge. Do not keep on idealizing that, guys. nice systems. Okay, now little bit more interesting, we will go to cyclic systems. Okay, cyclic system, drawing cis and trans is little bit interesting. Okay. Take cyclic system. Before getting into cyclic system, I will tell you some cyclic compounds, or you can call just cyclic systems, whatever it is. We will just ask ourselves, we will start from the smallest ring, cyclopropane. Cyclopropane, how it exists? How it exists, cyclopropane? We can say, like, I can put you cis and trans here. What is the stable form of cyclopropane? How it exists? Can you see trans cyclopropane? That is why I am asking. So, you can see only cis, right? The trans is can. So, do not think if I put a cyclopropane alkene and you do cis and trans of it. That is why I want to give you before we do the problems. Fine. Cyclobutane systems. Trans, no trans. Okay, very good. Cyclopentane. We are coming near to the borderline. Okay. No trans. No trans by photochemistry, or you can see trans somewhere by eating or something. No trans. Sure. I am just going by you. Okay. What I feel is that there is no trans in photochemistry. Trans is there. You cannot get your trans in photochemistry. That is what I heard about cyclopentane systems. But you do not see trans cyclopentane type of trans, any examples, any derivative of cyclopentenes. Okay. Trans is there, right? You trans, you see, you do not see in photochemistry. Okay, that is particular. Fine. We cannot make a trans photochemistry, trans in photochemistry. Fine. Then we can get in your cyclohexene, that is 6 membered, as well as your 7 membered. Yeah, you can say that trans is always there. Okay. Cis 6 and 7. Trans you can get. Okay. Oh, sorry, cis is always there. Sorry. Yeah, trans. Trans is there. No. Yeah, but I can give you an examples. Okay, where you can see trans systems in 6 member rings and 7 members ring, but the lifetime of your trans is very less. It will be 9 microseconds, 10 microseconds, and people have trapped the transform. We will see that examples. Just before getting into the examples, I want to make sure that we know all these things, then we will get into the examples. Okay. So, there are many examples where I will give you a system where you can see the trans of your 6 member ring, and that has been even trapped and isolated, and the lifetime has been around 9 microseconds. Okay. 8 member. Yes, you can take both, both and even they are isolated. Okay, 8 members, that is good. So, now as we move on, then you can keep on getting things, fine. So, up to this you should have an idea, like you have 3, 4, 5. So, the borderline becomes around like 6, 7, 8. That is good. So, now we will get into examples of cyclic systems and see whether we can draw really cis and transform of it. Okay. Okay, I have a system like this, I photolyze. Now you have to write the trans of it. How you write it? Can you think about writing a transform of this? You're written. That's good. See, the best way is that always keep your double bond in the linear, in the plane, then draw the rings. Okay, that will be easy. Like that you can keep. Okay. Yes. Fine. So that's why you keep your double bond in between, okay, in the plane. Then you draw, then you get your cis and trans. You can move according to, you can move your phenyl down or you can move that. The lambda max of this particular compound is 380 nanometer, and the lifetime, the transition lifetime of this is 9 microsecond. This particular compound, the transform of it. Okay. See, if you take a system like if I take this in the presence of a system like taking this, okay, sorry, I am not having double bond here. If I take this and photolyze together, okay, I am taking your cis form and taking my type of aromatic cyclic scene, okay, and photolyzing them together. What happens is that once I get my trans, okay, this form, what do you expect? You can write like this, or if you want you can write in other way, which you can write symmetrically like this also. It is the same thing, you can write in a symmetrical form like. Okay. What do you expect then? That is more important. At least write like this also. Nah, what you are going to expect? These two are now right in the. I take a cis, photolyze, it will go to trans, then I have a system like this. Anything, any idea what it can happen? I have studied these reactions. Yeah, you can aptly do a 4+2 cycloaddition, right? Your Diels-Sader type of reaction, you can nicely form a 4+2 adduct. So, can you draw the structure 4+2 adduct? It can undergo a nice 4+2 reaction. Okay. See, people are trapped it, so clever they are. See, 4+2 goes much more faster than your 2+2. 2+2 symmetry is not that much allowed. Okay. 4+2 happens very fast. That is the only reason. Okay. 2+2 in photochemistry you can see a lot. But 4+2, if it is there, more possibility of 4+2 is there. You can do 2+2, there is nothing wrong with it. Fine. Which one? These are the reactions, you can get it. Yeah. We will see, we are going to get that, okay. Do not worry, we will see all these reactions. There are many rules where you can get it. So, what product you have written? Anything nice? So, I can use this double bond. Okay, there's little bit change in the double bond. Okay. Yeah. So, I get a system like this, 4 plus 2. So, what happens in this case, this your aromaticity should come back again, right? Your aromaticity should come back again. So, you have a system like this. Now, just think of doing 1,3 hydrogen shift from where? See, I want to push this, okay, this nitrogen here, I can move here, so it can become an aromatic, so I can do a 1,3 hydrogen shift, then it becomes a very stable molecule. Right. So, this type of products have been isolated. Okay. This tells you that yes, there are systems which can be, okay, you have 6 membered, you can think of forming trans. Okay. This you can, trans people have taken it, they have found out their lifetime, transition lifetime, and same way they have isolated the products. Okay. You cannot take directly trans isolated, that is very hard, but trans are formed in photochemistry. Clear? That is good. Now, we will go to our next example, which is type of 8 member ring. Okay. If I fertilize this, now you know to write the transform, right, pretty well. So, just I will use this one. Okay. Sorry, just write by yourself. Three. You can write this and then you fine, good way of writing it, just like your 6 member. I just try to write your 8 members. Some people even try to write like this. If you want, you can think of this way. This way also people write, okay. But if you can keep your double bond, most of the time it will be helpful for you in many structures. You can keep your double bond ideal, but it's this way also you should know, because if you have a system which is having 2 double bonds, okay, then you cannot use this way to write. Then you have to go to this way to adapt. Okay. This both are symmetrical. The same. Okay. So, that is more important to draw structures like that. Okay. Now, we will take another good examples of second. What is this? So, now we were dealing about one system, okay, one alkene system, one double bond system. Now, we are dealing with diene type of system. You call this as butadiene, what form it is? Yeah, how you call butadiene trans, how you call them? Yeah, transoid, right? Most of the time you call them transoid, cisoid, because if it is trans, then I can put my double bond inside and put 2 radicals here. Okay, that will become trans also. So, it is more like a transoid, right? That you should know when you differentiate between diene systems, transoid, cisoid, that is the word you use. Okay, alkene you use trans and cis, right. So, then you can draw this you know how to draw, that is fine. So, I am fine, I am not worried about that part. Now, if you are given a system like okay. Now, I am giving a system which is like this, it is a diene again. Now, I photolyze. How you think about drawing this? This is much more interesting, because this is planar structure. Yeah, you did a cyclic, so it is easy to write a trans and cis to this. This form, better way of projecting it in another form, looks to be a simple molecule with a diene system. Yeah, draw by yourself. That will be that will make you to think. That is what I want. How you are putting a double bond, if it is like that, that is what I am looking for. How you are placing your double bonds. You have studied that. That is why I am just taking your basic knowledge of understanding. You have studied. See, basically what you can do is that you know how to put this double bonds. No? That is all. It will tell you other things. From that you can always go ahead. No? Because you are taking this system and you are written like that. So, it is easy. Then you can finish it off. See, this type of structures you can see when you go for your alkene type of pi star chemistry. This all happens. These are all been isolated. That is the part, is that it is not that this is the product which has been just you are drawing by theoretical. No, these products have been isolated, taken out, characterized completely. So, that should be the idea when you think about cis and trans systems. Drawing cis and trans is little bit, you should be knowing them how to draw. Better understanding of the structures.
So, will these two structures equilibrate?
Yeah, sure. These are all the systems. Most of the time, you know your transoid, cisoid, even that is equilibrate. Yeah? You take your butadiene, you keep it in solution, you exist both your trans and cis form in all the time. Okay, it is not like you can take your trans form out. This is a famous compound, right? This type of azo compounds are made lot, and you have studied any famous azo compounds which you know, like this type of rings which have been used as a very good base. DAPCO, diaza bicyclooctadecene. Okay, you have DBU. And diaza bicycloundecines. See, these are all molecules also you can think about. Okay, just I am taking, that is why I take one example of azo compound. So, how to write this? Whenever you write azo, it's always nice that you say I am not written this here, but whenever you write azo, it's nice to put your lone pair of electron. Okay, and show how this lone pair electrons are cis and trans. That's also nice way of looking at it. Yeah? That's how you study. One, two, three. 1, 2, 3. Right? Okay, that's good. What is this molecule? Can write like this. Seen this molecule, studied this. Furyl. How you make this? Any idea? How you can make this? Condensation. Yeah, it looks to feel like difficult, but it is easy molecule to make. Of what? Hey, you guys studied retro, just leave it. That's all you end up with an aldehyde, right? These are this compound is very interesting. If you just go and see what happens to this. Yeah, you can do that. Yeah, there are many methods available to make these molecules, but they are interesting molecules. If you do the photolysis, yeah, you end up your so that's so these are some of the cis and trans isomerization which you are seeing. Any idea why your 3-membered and 4-membered doesn't form transform? Ring strain. Sure. If I go to 9, 10, what happens? You can isolate transform. Okay, that's good. So that's fine. So that's how to start with alkene photochemistry. What I am going to try in next class is that we will be getting into your type of dimerization reactions. Okay, where we will be you have a system like this, particularly with butadiene type of systems. And in this case, what happens once you photolyze, it undergoes a cis and trans isomerization, but at the same time you have more chemistry happening from dimerization. Okay, that we should be knowing. Yeah. So what we do is that we'll stop here and we'll say that we have finished one reaction, that is your cis and trans isomerization. Next class we will start our dimerization reactions. Okay.